Hi, welcome to the Semantics lecture about set relations. Now, sets are very interesting objects because they contain a number of things and we can abstract over them and create properties and so forth. But they're also interesting by the way that they relate to each other. So take, for instance, a set like this, 1, 2, 3. We can draw a circle around it and give it a name. We'll call it set A. Now, if A is set 1, 2, 3, it doesn't tell us much. That's just the set. Well, let's draw a second set. I'll call it set B. And set B also contains 1, 2, and 3. Maybe it doesn't contain them in the same order, but it contains the same objects. Let's say 2, 3, and 1. Well, because A and B contain the exact same elements, they are identical. And we can express that using the equal sign. We can say A equals B. And that only applies when they have the exact same numbers. Now, what if they don't have the exact same numbers? Well, let's draw a set that just contains 1 and 2. We'll call this set C. Now, set C has members 1 and 2, but it is not identical to set A because it doesn't have number 3. We say that C is a subset of A. And we say that because every member of C is also an A. And we can express that using this symbol, a horseshoe with a line under it. And the open end of the horseshoe points to the larger set. So this is C is a subset of A. The horseshoe says this is bigger, and the horseshoe says that every member in C is a member of A. The line says that it could be this case that C and A are equal. That is to say, if C had all the members of A, it would be equal to A. But by this definition, it would also be a subset. Now, if C is a subset of A and A equals B, then we can conclude that C is a subset of B. So that's the subset relation. The converse of that is the superset relation. When A is a superset of C, it means that every member of C is a member of A. Or, to put it another way, C is a subset of A. So we can write it like this. We could typically read it left to right, though. So we would say that A is a superset of C. Now, in the case of C, we can say that, you might be wondering, with the subset or superset symbol, why bother with the line? Well, in this case, we happen to know that C does not have all the members of A. And we could write this without the line as a result. This would indicate a proper subset. That is to say, C is, every member of C is a member of A, and they are not equal. This is only true if A has members that C does not. Likewise, A is a proper superset of C if A has members that C does not, but every member of C is an A. And anything that applies to A will apply to B because they're identical sets. Okay, so that's subset and superset. Now, for sets that are not identical, one can be a superset of the other, but sometimes we have sets neither of which are supersets of the other. And in that case, we want to see, do they share members or not, and so forth. Now, when two sets share members, but neither is a subset of the other, we say that they intersect. And we can even define a set called the intersection of the sets that involves every element that's in both sets. So here's an example. let's say our set C. Set C again. Elements 1 and 2. But let's define a new set. Let's call it D. And D has elements 1 and 3. We'll write that over here. Now, if C has elements 1 and 2, D has elements 1 and 3, neither is a subset of the other, because each has members outside of the other. But they do share a member in common. And this member is their intersection. So, we can write this in a very, we have a symbol to write this very simply. It's called a cap. It's like an upside down horseshoe looking thing that faces down. So, C, D. And this is read the intersection of C and D. And in this case, it is the set containing 1. Right? Because the only member that contains it, the only member that's in both of these sets is 1. And you can think of identical sets as two sets whose intersection are themselves. You can think of subsets in terms of intersection as well. If C is the subset of A, then the intersection of C and A is C. So, the intersection of A and C is just C. Why? Well, because A is 1, 2, and 3, C is 1 and 2. So what are the members in both sets? It's 1 and 2, which is C. So whenever we can redefine the subset relation in terms of intersection. And we can also redefine intersection in terms of a subset relation. And that's a kind of interchangeability that we can use to our advantage. Now, that's the intersection. We can also, when we have two sets that neither of which are the subset of the other, we can take two sets, well, actually we can take any two sets, and we can create a set out of every member of either set. So the intersection is the set out of every member of both, and what we call the union is the set of everything in either. So, recall we had C and the intersection of C and D is the set containing 1. It's the only thing that's in both. But what is the set of things in either? Well, we say that's the union of C and D. We use this U-looking thing called a cup. And we say that that would be 1, 2, and 3. That is to say, element 1 is in either set, 2 is in either set, 3 is in either set. And in that case, we get a nice distribution here. And the union will contain these items. The intersection is more restrictive. Both of those will be useful concepts. Right, so, we can expand our universe a little bit. Instead of simply having 1, 2, and 3, let's add a couple of Greek letters. Here is phi, and here is psi. And so now we have, let's add gamma. Here's gamma. So psi, phi, and gamma, 2, 1, and 3. Now we can form sets out of this too. Now let's say that we create a huge set and we call it Z. Now Z is going to consist of 1, 2, 3, phi, psi, and gamma. It's going to have all 6 of these objects. That's a big set. Now, if we take A, all right, A is going to be 1, 2, and 3. Now we could take a set as well, just of these Greek letters. We'll call it set Y. So Y would just be the Greek letters phi, psi, and gamma. Now, if we took the union of the union of A, right, which is set 1, 2, and 3. If we took the union of A and Y, we would get Z, because we would end up with all these members. And we can write that. We can say that the union of A and Y equals Z. Now, what if we want to talk about the things outside of the set? Okay, and that's where we get the notion of complement. So the notion of complement is pretty straightforward. It's the members within one set that are not in the members of another set. So a complement requires these two sets. So here's A, here's Z. A is a subset of Z. And when we want to talk about a complement, we want to talk about the members of the superset that are not in the subset. And as we say, that's the complement. And there are different ways to write it. A simple way to write it is the minus sign. So you take the larger set minus the smaller set, and that will equal, in this case, y, which is this. That is to say, it's going to be all this. If we take z minus c, then we get the union of y and the set containing 3. And you can work out how that works. But a complement is just the part the complement between a superset and a subset is the part of the superset that's not in the subset. And strictly speaking, we'd say the complement of A in Z is, say, the complement of the subset in the superset. So we have these different relations. There are a lot of exercises and ways to figure out how these sets work together, but essentially they all work in this, this is basic different kinds of relations between these sets, and they're very useful. We'll see them throughout this semester. We'll see them throughout forever when we're doing semantics or logic or all sorts of kinds of math. So we have identity, subsets, supersets, complements, intersections, and unions, and with that we can put sets together in very powerful ways.